thanks, and now for something completely different. I'm going to talk to you about the world of high-temperature electronics. And as Pat Gilsinger said yesterday, semiconductors are our superpower, and I hope you learned today that high temperature doesn't have to be our kryptonite. So at Ozark IC, we began developing high-temperature electronics back in 2011, starting as a fabless design house. And what we quickly learned was that solving this electronics problem outside of standard specifications and requirements requires some different thinking. Tight integration across materials, integrated circuits, packaging of systems. But working down this path leads to not just doing designs based on predefined rules like we were kind of all learned in school, but embracing the whole system and supply chain, including the packaging and ultimately the manufacturing to solve the complete system problem. But if you do this, you can bring computing to the edge and in some pretty extreme places. And this brings us to our challenge. What problem were we trying to solve with high temperature? Well, how do you sensor control in an extreme environment? So imagine trying to control a jet engine, trying to steer a drill underground for energy exploration, control a nuclear reactor, or even maybe land a vehicle on Venus. These are places that are very hot with extreme vibration and likely radiation as well. Most electronics we have today simply can't take the heat, and the current solutions seen here, they tend to be very custom, very expensive, or in some cases they don't exist. We don't know what's happening. So why is this? Well, as you can imagine, most of our electronics are based on silicon. And silicon has practical limits to its operation, based largely by its leakage, its band gap, and how we interconnect on it. As a result, our standard temperature ranges for electronics have been quite limited. 125 C is probably a temperature spec that a lot of people in this audience are familiar with. This in turn has limited everything around the electronics. This means the packaging, the chips, the connectors, the integration, the whole ecosystem has been limited. Everything has to work together. So moving to high temperatures means we have to look at new materials, but we have to also look at all these aspects together. And this requires the development of new standards and methods to validate them, as we're going way, way off the end of the temperature ranges that we're all used to. So, where is the mission? Well, we're here at the high temperature basically enables speed, and new trajectories and profiles not possible for. And with hypersonics really being at the bleeding edge of this in terms of mission and speed and need. But at the intersection here of mission and commerce, what we find is that high temperature follows energy, and energy is what makes the world go round, and that's why we're here talking about high temperature for clean energy. So high temperature electronics for geothermal wells at 400 to 500 degrees Celsius are needed to require reducing drilling time and cost for energy exploration. But more importantly, this opens up reserves beneath our feet that could power the entire country if we can only access them. New modular and molten salt reactors are in development that will operate at 700 degrees C of the molten salt coolants. And we need sensing electronics to maintain the health and monitor them. And both of these technologies would directly impact sources that are currently generated by natural gas. In energy storage and conversion, high temperature electronics enables full utilization of our green power sources. We can put the conversion electronics much closer to the point of use. And all these together can affect up to 50% of our global greenhouse gas emissions. But even more importantly, in commercial aviation, we all want to travel, and we want to do so sustainably. In a commercial jet engine, you can see everything from ambient to hundreds of degrees Celsius at the exhaust. High temperature electronics means high temperature control. This means weight reduction, but this also enables us to allow the use of new alternative fuels like hydrogen. And 3.5% of our global greenhouse emissions come from global air transport. But even more importantly, why is all this digitization so important? Well, without knowing the conditions in these environments, we can't make use of the emerging AI and machine learning technologies that we were learning about this morning. We can't deploy them. And so the way I see it is there really is no frontier that we can afford to not digitize to enable the data that will enable these technologies. So what's the state of the art? What are we able to do today? There we go. So silicon can actually be pushed much higher than mil-spec. Using advanced silicon electronics, high-temperature design techniques, and advanced ceramic packaging, silicon can operate at peak temperatures from 200 to as high as 350 degrees C. As seen here on one of our 4 megahertz 32-bit single-board computers operating under test on a turboshaft engine at Virginia Tech with DARPA support. Our 100 megahertz 32-bit single-board computer has been operated for over 7,000 hours at 200 C, acquiring digital data the entire time. Silicon on insulator technologies with proper design and enhanced interconnect can get higher performances. But to get even higher, we've got to look at novel semiconductors. So going even higher, silicon carbide technologies invented and developed by the NASA Glenn Research Center are sort of one of the gold standards for high temperature reliability. We've combined these with our own high temperature packaging and design techniques, and we've shown that these can operate at 800 degrees C for 50 hours or more. And these are integrated circuits. These scale from simple amplifiers to complex digital logic. As shown here, these electronics using additively manufactured ceramic packaging have proven robust enough to operate for over 1,000 hours continuously at nearly 500 degrees C while driving a DC motor. Our silicon carbide electronics have been flown in orbit for over a year as UV sensors on the International Space Station, and they've also been successfully tested on turbine engines up 450 C. They are tough, but challenges and opportunities still remain. So taking these technologies further requires advances across the table. We're at a place right now where we're able to perform at the hundreds of megahertz at 200 degrees C using silicon. Moving up in temperature, we're poised to scale in complexity, such as the multi-chip RISC-V 32-bit 500C processor in development shown here, based on silicon carbide. We currently can digitize or electrify really any high temperature domain, but there are performance trade-offs. The next frontier is clearly to improve this performance. From AI to cybersecurity, all applications are demanding more analog and digital performance. For this, we need to leap ahead in transistor performance, all while increasing density. New wide bandgap and ultra-wide bandgap technologies offer tremendous promise. But the systems have to be designed as a whole: semiconductor, package, and integration, if they're going to survive and thrive. This requires that new thinking that I started the talk with than we've traditionally had in silicon and other related technologies, where absolute performance and volumes were king. This requires us all to work together, from fundamental materials development to semiconductors, modeling, design, packaging, yes, and definitely test, and developing those new standards that drive this new area of rugged computing and electronics. And just as importantly, just as with defense electronics as a whole, high temperature is a supply chain challenge. The supply chains for standard silicon electronics don't typically align with the needs for high temperature, often in terms of interconnect and most certainly in terms of packaging and, of course, volumes. Bridging these gaps requires many of the same concepts being discussed here this week in all defense arenas: chiplet-style heterogeneous integration, additive manufacturing, with the added materials complexities of high and wide temperature, cyclical and static, are all areas that have to be invested in areas of active research in addition to the semiconductors themselves. So I hope you learned today that high temperature electronics are capable of bringing computing to the edge in extreme environments. By tackling the semiconductor materials and design challenges, we have the opportunity to solve not just defense needs, but critical energy challenges that will secure our energy future. So I think it's time for all of us to stop worrying and start to love the heat. Thank you.